Good afternoon. It's actually a pleasure to be here at least virtually, at the SPIE Lithography Conference. It's a meeting that I have a close personal connection with, as I used to be a microlithography engineer many moons ago and attended this meeting for many years out on the West Coast. And it's nice to be able to come back here, although my role is a little bit different now, working at a strategic think tank. But I thank Eric Panning and the SPIE folks for inviting me to give a talk. I'd like to start out with a brief outline. I'm going to tell you a little bit about myself, a little bit of bioinformation, and what I do, what the think tank is, the Potomac Institute that I work at. I'm going to talk about the end of Moore's law scaling and the post-Moore future. That's the main point of what I'm making. What kind of new applications and business models are a result of the Moore's law coming to an end? And some major paradigm, we're on the verge of some major paradigm shifting, providing drivers for new low volume patterning applications and a complete change in business models. So here's my quickie bio on this chart. You can see that I've been mostly a technical person in the microelectronics area, and with stints at MIT Lincoln Laboratory, did a tour at the DARPA MTO office, managing a bunch of microelectronics related research projects. Then did a couple of years at the USC ISI, working on electronics projects primarily based for government sponsors. And more recently, in the last 5 years, I've worked at the Potomac Institute for Policy Studies, where we use science and technology to do strategic policy advice to senior government officials. So many of you are probably asking what a think tank is, so I want to spend a quick moment explaining what the Potomac Institute is and what they do. There's quite a few think tanks in the DC area that help make government policy. We're a particular flavor of think tank that I want to emphasize. We focus on science and technology, and the kind of think tank that we are is that we are independent, so we do not take commercial sponsorship. We just work for government agencies. That makes us our opinions independent of financial interests. We are nonpartisan and we are nonprofit. So we strive to be an honest broker to provide strategic advice on science and technology policy to the United States government. And just some of the representative studies that we've been involved in the past are pictured here on the bottom. So this chart shows some of the recent microelectronics work that the Potomac Institute has been involved in. We do a lot more than microelectronics, but my particular niche at the Institute heavily deals with microelectronics. So in general, our Institute works on bold ideas to look at national technology policy interests. You'll see here a bunch of different studies. I'm not going to walk through them all, but basically I'd like to just quickly cover the topics that they address: the sale of the IBM Trusted Foundry to Global, how the government should do state-of-the-art foundry access, the role of public-private consortia, the research industrial base and its health in the United States, how you quantify security and trust in ICs, what the end of Moore's law means for the future of the industry and government policy, and also what government acquisition policy changes can be made to improve their access and timeliness to new technologies. So this is a chart that I'm sure everyone's familiar with, but it's worth looking at since it's the motivation for a lot of what I'm going to say. It's quite clear that scaling piece by piece, the various aspects of scaling, according to Denard, have come to an end. And this one quite graphically shows, when you're looking at most of the performance parameters, technical performance parameters like power and frequency and single thread performance, etc., have topped out some years ago. We're still increasing the number of transistors, but not necessarily the performance. So that's actually very important. We're starting to face issues with the limits on multi-core performance. Dark silicon, you can get a lot of silicon as long as you don't actually use it in terms of power. And now we're looking at a situation where we're not getting a giant performance benefit from scaling. So what's the next step in terms of continuing on Moore's law and continuing to get performance? That's very important, and I'm going to say a few words about that in the presentation going forward. So this next chart here shows some economic data in contrast to the technical data that I showed in the previous chart. And you can see here, as we go below 45 nanometers, we really have a flattening out in terms of the costs for gate. And that's something that is historical in Moore's law, where we've always gained a cost advantage per gate as a function of scaling. And there's been a number of studies, this is one of them here, that shows that that's no longer the case. And that's actually very important in determining what's happening here as the scaling comes to an end. This cost curve is flattening out. We get less economic benefits from scaling. We're getting more transistors, but less economic benefits. The nodes, of course, we all understand. When I was a young engineer, half pitch had a specific quantitative meaning, for example. Now the nodes have less and less physical meaning, and they're really much more of a marketing term. And these kind of economic forces that you can see in this chart are kind of signal the end for the traditional scaling-based approach to Moore's law. And so what's going to come after that and what kind of patterning technologies are needed to support that is what I'm going to cover in the rest of this talk. So one more piece about the end of Moore's law. This is a dramatic chart that I particularly liked about the time between nodes. There used to be sort of the standard 18 months in between nodes, and you can kind of see that in the left-hand side of this graph. And as you start to move along to more modern times, to like 2019, 2020, actually starting already around 2012, you can see there's longer and longer periods between nodes, which definitely tells you something is happening. This is a clear sign of the end of scaling, of Moore's law scaling. On the bottom of this graph, I put the number of fab companies that were building logic as a function of time. And as you can see, as the nodes become more and more advanced and the time between nodes becomes longer and longer, there's less and less fabs. So we're starting out here in around 2001 with 19 fabs, and then we're ending out in 2020, 2021 between, depending on how you argue it, three or two fabs are all that's left at the state of the art. That's an important indicator of a paradigm shift approaching. So what happens when CMOS becomes a durable item? Well, there's a nice graph here on top that shows this. Traditionally, you really didn't have to do much in design. In a way, you can say the designers were allowed to get lazy because every 18 months or so, you had a new hardware generation that came out, and with the exact same design, you got much better performance in a cost-effective manner. Well, that's no longer the case, and so there's more and more gains, as you can see in the yellow here, that happen by innovation instead of hardware scaling. And this is going to cause a new trend in the business model for the industry that I'm going to talk about. So basically, it's the designers, and I have them represented by the hard hat people down here on the bottom left. It's the designers that are now going to provide the value in this enterprise, and the CMOS itself will be pretty much the building blocks or the bricks here that I have in the lower right with the trowel symbol. So this chart shows a dramatic example of what happens when an industry is getting mature. It basically shows consolidation, and this is an inevitable feature of the consolidation of the industry. You can see here, starting in 2001, there were at least 15 or more fabs that were able to do pretty decent state-of-the-art CMOS. And as we move down here to more modern times, so with global foundries leaving the scaling situation around 2015, 2016, you can see that there's pretty much only three left: Intel, Samsung, and TSMC. And there's a lot of press out right now about Intel outsourcing some of its production to TSMC. So who knows? In the future, there may even be less than three. So this is an important sign of industry consolidation. These very few fabs are going to be left that can do state-of-the-art. They're mostly in Asia. And TSMC of this lot is the only one that's really a pure play state-of-the-art foundry. That's important when it comes to thinking about the future of the industry. So let me say a few words now about market saturation, because that's actually very important in semiconductors and what's actually driving the market. When I was a young engineer, the typical drivers for semiconductors was the PC, for example, right? And there was a standard curve of how long it took people to adopt the PC. More recently, the cell phone, the mobile phone, has been a main driver. And you can see at the chart on the right that we've really nearly approached saturation here for the cell phone market. So we're not going to get the kind of growths that we've gotten in the past, and that's certainly also true for the PC. I put a little history on here to show you what's happening with technologies. If you look at like the telephone and automobile, electricity, you can tell it took many, many years for saturation to occur. And if you look at this graph here on the left-hand side, you can see 100% is on top, 0 is on the bottom. And as you get to more modern technologies like television, microwave, and you go over to the cell phone and the internet on the left-hand side of this graph, you see it gets faster and faster. So that actually shows you that the modern markets and the modern application drivers saturate quicker and quicker. That's actually very important as an economic driver for the industry. In addition, that puts great pressure on new applications and new technology capabilities because you have a more limited time before you reach saturation, and people won't be you won't be on the growth curve of the technology anymore. So what does the end of Moore's law mean? Well, in one sense, it's an indicator of the maturity of the industry. As industries mature, and you can see some mature industries here on the right-hand side, the automotive industry and the airline industry, for example. Well, microelectronics is not immune to maturing like those industries have. And this end of scaling, of Moore's law scaling, really represents a migration where microelectronics will be changing from a commodity which typically has a rapid refresh rate to a durable industry where there's a much slower refresh rate, and you're adding features primarily in design and in other areas, and you're no longer scaling the hardware. So that has a lot in common with some of these other industries. Well, as an inevitable consequence of these kinds of maturities are consolidation. That always happens when an industry becomes mature. So you're going to have less players, and you're going to have them more focused on cost optimization, just like these industries here on the right. We're going to be changing in business model for semiconductors. In the past, we had very high volumes of broadly applicable generic consumer parts, parts that could be used by different industries and for different applications, like processors are an obvious example, but even some of the early AI hardware, like from NVIDIA and others, are broadly generic. So those were made in very high volumes. Now the future, we're looking at a lot more custom parts made in lower volumes, and I'll talk a lot more about custom parts in the future of this presentation. But this also means, since I do a lot of thinking for government policy, it means that the government and the DoD can now become a serious player again because there's a lot more interest going to happen in customization at lower volumes. It also means that the fabless design houses will be leveraging the very few remaining state-of-the-art CMOS foundries, and they will really be commodity durables, providing the bricks, so to speak, for the designs that they execute. So what's going to happen with the maturing of the industry? Well, one of the trends that we see is a brand new and unprecedented role for the system companies in the semiconductor industry. In the old world, you had a situation of foundries and IDMs, right? So you had your foundries building your chips, your IDMs building and designing chips. A lot of the designs, most of them, in fact, were executed by these folks, and they provided generic parts for the systems folks to leverage, and they bought them from the foundries, basically. In the new world, and I represent the new world with companies like Google, Amazon, Microsoft, Facebook, etc. Now you have system companies that are becoming very interested post-Moore in custom solutions for their needs. And this means that they've all been moving into semiconductor chip design. All of these companies, and I'll say a few words about this coming up, all of these companies have chip design teams, and they're starting to build their own chips. They're starting to design their own chips. And well, the foundries are actually building them, but they're designing to design their own chips that are custom, instead of buying these chips from the generic providers in the past. This represents a major shift in the semiconductor industry. So what kind of chips are these new system companies working on? I must say that this is rather an unprecedented trend, as these companies typically bought generic high volume chips from others. And now they're realizing, especially with the growing AI applications coming around and cloud server applications, that customization will benefit them tremendously. So they're all getting into the chip design area, which historically they have not done. So let's review a few of these as we move down. So Google is working on custom AI enabling chips. We've heard about their tensor processing unit, for example. They're also exploring artificial intelligence applied to chip design to shorten the cycle time for making custom designs, and they're working their own CPUs as well. Similarly, Amazon is working on rapid custom chip developments for the Amazon Web Services, working with ARM. They're working on custom hardware for data centers and also on cloud EDA. Number of chips coming out include the Graviton, the Nitro, and the Inferentia, for example. Microsoft is also working on custom chips. They're working on a custom security chip for Windows called the Pluton, and server chips, custom server chips for their cloud-based data centers. In addition, Facebook is also working on custom chip designs based on some Google hires that they've made recently. And they're targeting also artificial intelligence and virtual reality. The number of chips that they're working on include the Xeon, the Kings Canyon, and the Mount Shasta chips, for example. And finally, Apple is also working hard on developing their own custom chip designs for the iPad, the iPhone, and the Mac CPUs. Basically, all of this is indicative of a trend towards more custom, lower volume parts, in this case for AI, made in state-of-the-art technologies. Talking about the new business models for lower volume patterning, I'd like to refer to the McKinsey report, which has a lot of really good conclusions and good data in here. This one is based on the artificial intelligence hardware. They looked at this as a paradigm shift, creating a whole slew of new opportunities for semiconductor companies. And I'd like to walk through these for a second because they are quite important. Historically, only 20 to 30% of the profit from a particular application actually went to the hardware people. This is actually changing now in the post-Moore world, right? Now we rely on custom hardware as a core enabler, which is very, very important, instead of the software, which has made most of the money in the past. So this means custom hardware companies can now capture in their conclusions here up to 40 to 50% of the total value. This is a big shift in the opportunities for hardware folks, and the role of custom patterning is going to be very important in getting these hardware folks to get successful. So basically, the thing I'd like to leave you with on this chart is the conclusion that they make, which is to undertake a new value creation strategy that focuses on enabling customized end-to-end solutions for specific industries or microverticals. That's very important. This means an entire new industry based on making custom hardware, which I argue is going to be made in lower volumes and going to require low volume patterning technologies. So we've talked about some of the new application drivers. The previous chart with the system company activities were primarily focused on AI and cloud and data centers, and you see them reflected here on this list. But that's by no means the only drivers for the future and for the lower volume customization that I'm talking about here. A number of other drivers include the Internet of Things, and I need to emphasize here that that is certainly not state-of-the-art technology for the most part, and that's driven a lot of the resurgence of 200 millimeter fabs, for example. There's virtual reality and artificial reality as another major driver, and of course we all know from the recent shortages, the automotive industry is also very heavily reliant on chips, and once again, these are not state-of-the-art chips here. I have the hype curve listed here on the left to show that each of these will go through their own specific hype curve, and it'll be very interesting to see which of these will become the major players going forward. Probably all of them are well positioned to have big roles. I don't think we're going to have a single major player going forward like we've had with the PC or with the cell phone, but I could be wrong. Prognosticators always take a risk of being wrong. So basically, the final point I want to make here is that all of these drivers require custom solutions for lower volume specific applications. And the other point I want to stress is that they don't all require state-of-the-art. The digital processing ones certainly do, like artificial intelligence in cloud data centers, but others like Internet of Things and automotive do not. And so this increasing demand is not just for custom chips, it's not just at state-of-the-art, but also for older technologies. And that has a business impact on the capabilities of the fabs to deliver the market's needs. So what is the industry impact here of the increasing level of customization that we're seeing coming down the pike? Well, first off, there'll be a higher number of custom chips made in lower volumes, as I've already said in the past. This has a number of important implications. Are the large fabs today ready for this kind of a shift? Are they ready to make a really high mix, much lower volume kind of a production? Are they tooled, and are their processes tooled, and their technology tooled for that? There's also a new opportunity for the mature node, the specialized fabs, that'll bring them a lot more business going forward, and this could lead to some major business changes. There'll certainly be more opportunities for smaller, innovative companies. In the past, any clever designs were easily surpassed by taking an existing design and just scaling it by Moore's law. So the larger companies had an advantage, the people who could do scaling. Well, now when we're talking about customization, the smaller companies developing the custom IP have a big chance now to compete on a more level market, more level playing field. So that'll be very interesting. There'll be new design architectures leveraging rapid customization. So this will bring a strong commercial incentive for those companies that can deliver low volume customization solutions. That's a big opportunity for the industry and also for folks here in this part of the conference working on customized patterning solutions, for example. There will be an emerging role for specialized integration fabs. They certainly do. They don't need the state-of-the-art fabrication capabilities, so we're not talking about the giant, expensive fabs. We're talking about being able to specialize chips made in a variety of technologies, including state-of-the-art. So they themselves don't need to be state-of-the-art. That's a brand new business. And will that be the current large fabs or not? Remains to be seen. Finally, there'll be big changes coming from the open source hardware and the hardware as a service paradigms. Really a paradigm shift towards a more software-like business model. And this will have an impact on many things, including the value of IP, for example. So what are going to be some of the customization enablers for the examples that I talked about in the last slide? Well, number one, we're looking at new roles for specialized chip integration fabs. And what they do is take chips in different technologies, maybe from a large CMOS fab, maybe from a specialized technology in a small fab, maybe a different kind of technology platform from a third fab, and do the integration. Now, that doesn't require state-of-the-art equipment, so that's a completely different business and a completely different business model. This is going to be happening in the future as scaling comes to an end. And of course, a very important driver, and we're all aware of this in the lithography world, is the role of three-dimensional integrated circuits and interposer technologies or heterogeneous integration. This is one of the specific technology platforms that these specialized integration fabs are going to be using. And I like to note here that to do some of this integration, it doesn't require the state-of-the-art feature sizes. It does require advanced capabilities, but not necessarily state-of-the-art feature sizes. So it'll be interesting to see whether separate businesses form that do this integration or whether the previously large fabs are going to do this function by themselves. It's not completely clear, but I think there's going to be a role for specialized fabs personally. So the end of Moore's law is going to bring about a change in the business model. And one of the things that's going to be an element of this new business model will be an increasing role for high mix, low volume production. Now, your pure play foundries have been doing something like this for a while, although they really don't like the low volume, but they've had very high mixes in the past. And this is going to get even more so. And I argue that the lower volume issue will come in as well. So the whole foundry volume is going to evolve. The ultra high volumes are no longer going to be required. The process flow will be re-engineered in order to achieve this. And flexibility and speed to market will be key in order to remain competitive. Here's where I connect with this particular conference. Because of this, there will be an important role for new patterning technologies in order to enable high mix, low volume. Direct write has been developed for many, many years. I've been following it for decades in my own career, but there'll be new commercial pressures in order to that involve the advantage and benefits of direct write technology, especially complementing standard patterning flows. So there'll be flows that are optimized for high mix, low volume, and direct write patterning methods will be an important part of such flows. And finally, the increased role of specialized chip integrators. Well, I've already talked about the fact that they don't necessarily need state-of-the-art production, but they do need to provide flexibility and speed to their customers. So what other new aspects of the new business model can we talk about? Well, one is the increasing development of the concept of hardware as a service. We all know that software can be rented and leased as a service, and there's an increasing movement to do the same for hardware. And I would say that the whole idea of hardware as a service has both a technical and a business meaning. In the technical language, it means how to enable rapid customization of ICs. In this case, the value add is the design and the architecture. And the goal is to have hardware updates as easy as software. There's a couple of programs on this. The DARPA one is a good representative one, the software-defined hardware program, in order to make hardware almost rentable in the future as a service. And on the business end of things, how do you actually develop a business where hardware is rented, you're capable of rapid upgrades, and your capital expenses as a customer are highly limited. So there's going to be a lot of opportunity for developing businesses around this concept in the post-physical scaling future. So one indicator of these changes is the increasing interest in low-volume custom ASICs. Some year when I was ending my lithography career, there were less and less ASICs coming out, and they were getting more and more expensive, and people were shying away and going to programmable FPGAs and things like that. Well, based on the future, the post-physical scaling future, there's a much, much bigger interest in enabling low-volume custom ASICs, and I'd like to talk briefly about a number of programs in this area. The DARPA POSH program is an open source hardware program where they're developing open source hardware IP, an entire ecosystem, including verification. So they're making a serious effort in this direction. The CHIPS Alliance, I want to mention, the Common Hardware for Interfaces, Processors, and Systems. This particular alliance is looking at harnessing the energy of open source collaboration to accelerate hardware development. So this is another force, and I believe there's some collaboration going on with DARPA on this, on the power of open source. IMEC is getting interested in it in their Chip for Makers effort. And just looking around the internet a little bit, there's definitely a grassroots effort that you can see in the websites, blogs, and crowdsourcing on open source silicon and how to deal with making designs in open source silicon. Well, let's take a quick look at what's happening in the ASIC market as a function of time. As I said, people were shying away from ASICs in the past because they were getting very expensive, and there was a very, very powerful, inexpensive alternative with a performance hit, of course, in the programmable hardware or FPGAs. But if you look at this chart, and it's actually dramatic, the projected growth in the ASIC component of the market is actually dramatic compared to some of the more generic programmable chips like FPGAs or even the processors or GPUs. If you look at some of these projections, you can see that the ASICs are projected to grow dramatically. The percentage of ASIC production is projected to grow dramatically compared to GPUs, CPUs, and FPGAs. That is a major indicator that there's a change afoot in the move toward increased customization to function. So if low volume is great, why haven't people been doing it? Well, it's because of the fundamentals of economics that you really can't break. I include here the universal cost curve, which you'll find in every economic and acquisition text that shows the price per unit of whatever you're building depends on the amount that's produced because you can amortize costs. People know this. They forget that sometimes with custom military things that are made in low volumes, that you're always on this curve, but the truth is you're always on this kind of a curve. So if we are going to evolve the business model to enable low volume, high mix production, you basically will need a new process and patterning technology that allows cost-effective production to occur at low volumes. And that's not a trivial thing, and this is one of the challenges that I raise to the community here, is to work on these things in order to be able to make lower volume patterning more cost-effective. Because the economics is the dismal science. You're going to be on this curve one way or another. So in order to enable these new lower volume business models, clearly the costs of ASICs made in lower volumes need to be driven down. I show here a classical crossover curve between a customized ASIC and a programmable FPGA. And we all understand that ASICs start out much more expensive because of all the design and the overhead required in the beginning. And only when they're made in very, very high volumes do they start to look economically attractive. Of course, if we use new fabrication approaches, new fabrication flows, new patterning approaches that lower the cost of doing customization, then we can achieve this crossover occurring at much lower volumes. And that's actually very, very important in order to enable the business models that we predict here, that I'm predicting are coming down the pike. So let me move on to a few concluding words about the post-more novel patterning of ICs in low volumes. First off, we conclude here that the custom parts will be made in lower volumes. This is a major paradigm shift from generic parts made in very high volumes that has dominated the industry for many, many years. So that's actually very important. There will be new patterning technologies and there will be new business models develop around them. And that will be important in enabling the future. The patterning technologies will include direct write integrated into process flows. And I would also argue that process flows will be tweaked and tuned so that they become more cost effective to build a higher mix of parts at lower volumes. Business models will evolve as well, including hardware as a service, where you can rent your hardware, or you can even rent your chips and things and get them upgraded frequently. You can use open source hardware solutions instead of designing chips completely from scratch. A number of organizations we talked about are developing that. Um, there will be more fabless chip design using fewer and fewer state-of-the-art foundries, providing the bricks, the generic building block bricks involved here. There will be more of a switch to high mix, low volume production, and there will be a new integration focused fabs instead of the process fabs of the past. You'll have fabs that are focused on integrating a variety of chips and different technologies in a heterogeneous way. So getting this business model to work to enable a higher mix of lower volume parts is a very important part of the future. And I would say for this audience, an important, key part of that is getting the new patterning technologies that make lower volume patterning cost effective inserted. That's an absolute key. Finally, and because this is the world I work in a lot, which is strategy for government, there'll be a renewed overlap between commercial and government needs. When you have very huge volumes made for the consumer market, that really is a big mismatch between what the government or Defense Department needs. And now that the industry seems to be moving toward more customized parts, now there's a resonance again with the government and the DoD. So there'll be a whole new set of opportunities for collaboration with public-private partnerships and others. And I'm actually very bullish that there's going to be a lot of activity in these areas. There's all kinds of new legislation now in the Chips and Foundries Acts, for example, that just passed in the Defense Authorization Act that require that will represent major investments, government investments in the semiconductor business here in the United States. A lot of defense and commercial reasons to do that. So I'm actually very bullish about the future. We're living through an interesting set of times, but I'm bullish that a lot of good things are going to happen in this area, and whole new industries and new business models are going to develop. And thank you very much for inviting me to say a few words on something that we have a strong interest in here at Potomac. Thanks.